Ok. È la registrazione della seconda parte della lezione di 17 novembre. Qui abbiamo iniziato con binomio di Newton. In questo caso volevo chiedere se avete, diciamo, quando io prendo uno più x all'esponente n, questo significa io devo ripetere questo 1 più x quante volte? 1 più x, io lo ripeto n volte e mi chiedo, per esempio, quando ho x alla k, qui inizia 1 più e così via, arrivo a x alla k e mi chiedo qual è il coefficiente davanti x alla k, perché poi, ultimo, abbiamo detto che deve essere x alla n, ultimo, con coefficiente 1. Per trovare il coefficiente, io praticamente so che nel mio classe sono n elementi, io devo scegliere k elementi senza tenere conto dell'ordine, perché x prodotto di due numeri reali è commutativo, cioè l'ordine non importa. E quindi qui devo fare il mio elenco senza ordinamento, switch to English, ok. I am switching to English. Starting with binomial coefficient, I have to compute this coefficient, and this means I have to choose kappa elements from totally n elements without ordering them. Therefore, this shall be my coefficient m n kappa. That was, let us remind us, n minus 1, and so on. Last factor was n minus kappa plus 1 divided by kappa factorial. Actually, this can be represented very simply, n factorial divided by kappa factorial, n minus kappa factorial, because this product we already expressed as this one. Therefore, this is the expression for the coefficient in front of x alla kappa.
Professor, excuse me, I don't know if it's my problem, but I cannot see because there is a bad definition of the image. I don't know if it's my problem.
No, it's the same for me.
Yeah, let us see for the moment. Probably I shall do the following, shall stop all other I have the same problem yesterday. I have to close some. Okay. Okay. The only thing, no, this is wrong. Now let us start to clean this. Okay, let us see now the situation. Is the same?
Yeah, for me, yes, but I don't know if it's my problem.
In any case, I think in screen, it is okay. This means register everything. It is important the movie to be smooth. Unfortunately, I don't know, can you measure the speed of your internet connection? Simply you can use write in Google, Mr. Google, speed of internet and their application. If the speed is less than 2 mega per second, we have problem, because let us for the moment stop presenta ora il mio schermo. Yes. Okay, let me check my speed. Can you see my screen?
Yes.
Internet speed. Okay, Okla. I think here at the department, the rate is relatively high. Why? Okay, let my speed. Yeah, this is very good. 20 mega per second. Here is very good speed.
Is download which matters or upload?
Download is proportional. You see now. Yes, this is download.
I have 32 in download.
And this is completely sufficient. Then this should be a problem that too many users use Meet. You see, this is 40, 50 megabytes per second. So this is okay. Yes, I think we can stop sharing. We can continue. And I think the movie shall be okay. Because alternative solution is that I make registration in advance and you look at the movie during the hours of our, I can make in advance this lecture, and this is one possibility. We shall see. If the number of, if the speed is not permitting this, from tomorrow we can do this. I shall register in advance. Sorry?
Teams?
Sorry?
We could use Teams.
No, Teams is terrible. Teams for this resolution is worse. Be sure, Meet is better. I know very well Teams and the quality is not very good, but if you want, we try. Actually, I had big problems with Teams. But we can try. One solution is to register in advance the lecture, and then you can see, because then I can use Zoom, which is perfect, but cannot be used by our, how to say, during direct lectures by internet cannot be used, you cannot enter, but the movie of Zoom is better quality. Okay, let us see. Can you see now a little bit better? Or the situation is similar?
For a moment, yes, but then
let us see.
again.
Let us see. For the moment, I don't think to change to Teams, because this will destroy. We have 20-25 minutes more, and the lecture shall be lost. I prefer to continue, if you don't mind. For the moment, you say that you see better.
Yes.
Okay. I think this is connected with the fact that I opened too many applications. Okay. This also shall be closed. Yes, I think this shall be sufficient. Okay, let us turn to our treatment. So the coefficient in front of x to the power kappa, binomial coefficient, is given by this formula, and notation for this coefficient you can find in some books, n over kappa. This is another notation for the same binomial coefficient, that is n factorial divided by kappa factorial, n minus kappa factorial. This is the coefficient that in front of x to the power kappa. So it is coming from this binomial. Now, if we turn to our probability space, but before going, is it clear, this choice of the coefficient? We have binomial coefficient, that is exactly list of kappa elements among n elements, and with this choice we computed the coefficient. Did you try to use Teams? Some professor with you are using Teams?
All of them are using Teams, but they share.
Do you have problems to see? Resolution is good?
They use presentation. I don't know at the Blackboard.
This is much more. If I start this presentation with Teams, no, with some small PowerPoint presentation, you put too many things, but you can understand relatively less. You have easier thing to do with Teams, but I think it's better for us to continue in this way. If you prefer presentation, no problem. I can do this. It's also up to you. Okay, now we are going to the next step to understand a little bit the algebra of sets. Because we said that it is important to make union, intersection in our algebra. And in this sense, it is important, for example, to know the formulas due to the De Morgan. These formulas gives, if you take union, what is the complementary set of the union? So again, we have U and V inside omega, and you want to compute the complement of the union. And the Morgan formula says that this is complement of U, complement of U. But since here you have union, here you have to take intersection. The other formula that is important is U, intersection with V, complement. How you present? In similar way. You take the complement of U, the complement of V, and then if you have here the intersection, complementary set is union. So these two formulas are important for our next steps. And they show that, for example, probability of this set is equal to probability of this set. Also, probability of this set shall be expressed as probability of the union. Let us try to prove one idea of the proof of one. Probably this is very simple, but for completeness, we shall prove it. X, I have to show that if this set, then X belongs to this space. And vice versa. If X belongs to this set, belongs also to this. Belonging to U, union of V, complementary. What does it mean? This means that X is not in U, union in V. In fact, X in complement set, this means X is not in the union of U and V. Now we have problem with umbrella and array. What does it mean that X is not in this union? Let us make small picture. This is U, this is V. What we can write is the following. let us check this. This means that x is not in U and x is not in V. Let us try to understand this. So our x is here, outside U and V. Of course, it is outside of U and V. It is clear that we cannot have neither here, neither here. So x is not in U and x is not in V. It is important to put this connection. And why? Because we have also to say that what is not in U or x is not in V. Imagine we put here or. What can happen? X is not in U, for example, I can take x here. And you see, x is not in U, this is fulfilled, but due to this or, I don't care about this condition. Therefore, my point is outside the union, but the red one is inside V. And this means this is not, therefore, or is not good connection, and I have to ask, if x is outside the union, x is not neither in U, neither in V. And I have to put and. When you put and is always connected with this product. Therefore, from here we conclude x belongs to UC intersection with VC. Because his is in U, this means x in the complement of U and means intersection. In fact, remember that when you put for two sets, if you put A union of B, what is this? X they belong to A or X belongs to B. If I put intersection, this means X belongs to A and X belongs to B. So it was important to have this and. Therefore, our intersection becomes really in this way. So what we did, if x belongs to this set, with this line, we arrived here. Of course, we can go back. Say x is not in the intersection. This means x is neither in U, neither in V. So if our x is neither in U, neither in V, then x is not in the union, and then we are here. Therefore, De Morgan rule is simple. We have to know only the definition of union, intersection, and of course complementary set, and then you have this line that shows that these two sets are the same. Absolutely in the same way, if you have intersection, here you will have union, and you can freely use these relations. Let me stop for the moment to ask you, first, the connection now, the quality of the resolution of the screen.
A little bigger. Can you write a little bigger so we can see better? Because resolution is not so good, but if you write a little bit bigger.
Okay, but I think if this is worse than before or slightly better?
Slightly better, but it goes better and then.
Bene. Okay, let's go further. Other questions? Okay, So we have De Morgan formulas. And remember, these De Morgan formulas, they say U intersected with V, complementary set. Can you help me? What is this? This is, according to De Morgan, yes? How you can translate? If here we have intersection, this is equal to?
Union.
We have union of what? Complementary of U, complementary of V. And if you have, instead of intersection union, here we have to put opposite sign. So when you have here the key word was and this was and. Sorry, this was or. If put here you put or, then here when take opposite assertion, you put opposite word. Therefore, and opposite shall be or, opposite shall be and. Okay. Let us make the following example. Typical examples in probability are so-called dice, dado. So we have two dices. Example 1. We have dices. Do a die. Let us compute, for example, the following thing. Probability that exit, the result is, for example, first dice 1, second dice 6. Of course, when we have two independent dices, we draw them, and then we have to say, first dice, we have a result, and we write on the first place. Second dice, we take, we draw and put on the second place. Of course, this means we take into account what is first, what is second dice. First, in order to compute probability, we have to find all, define our space omega, all exits. Space of all, sorry, you asked me to write larger. This size is okay or?
Yes, thank you.
Omega, you have all possible m and n, where m and n vary between 1 and 6 integer numbers. And we took into account who is first, who is second. This means that again we have two boxes. How many choices we have for the first box? Of course, we have all numbers between 1 and 6. Therefore, here 6 possibilities. Since we said the second dice is independent, we draw it. Here, how many possibilities we have? Yes? For the second dice?
Second dice is also independent. Then we will get 6 combination for the second dice.
Yes. And totally, how many we have? The first place 6 possibilities times their independent. 6 by 6 is 6 by 6. 36 possibilities are all exits. one exit probability. This set is one element. We put as exit 1, 6. So this set is U1, and we apply assuming probability is equidistributed. Therefore, you have uniform, unique probability for one set of one elements. Therefore, probability of U1, we said this is 1 over this omega. Therefore, this is 1 over 36. Okay, this is simple case. And this means we have all possible exit 36. Now, let us take another set U, such that we have M n, but m plus n is 5. Let us how many, what is probability that the sum, there are some games where the sum of two results of the dice, the sum should be, for example, given number. You predict and you win if you have this number. So what we can do, one moment, let me switch the battery, because probably this also could be the reason for this weak quality of them. But more or less in the period, I remember that the best solution was to register in advance the lecture, and then you have the movie already prepared. We shall see. Now, all exits omega is still 36 exits. Let us see how many elements has this set. How you can choose mn such that sum is 5. What is favorable exits? Possibility. First is 1, second is 4. This is one exit that gives 5. Then we can have 2, 3. Then we have 3, 2. But again, 2, 3, and 3, 2, since we have taken into account first and second, they are different. In this calculation, we said it is important that who is first, who is second. And now count according to this, first, second. Then we have 4, 1, and that's all. So how many elements has this set? This set, we already computed exits such that the sum is 5, so we have 4 elements. And now we can compute probability of U. How we can compute probability of U? In this case, probability of our set U is equal, because we have equidistributed probability. This is our set omega, and here we have to count the set U. Now this set U has 4 elements divided by 36, and this is 1 over 9. Therefore, you can compute that the sum of the dices is 5. Okay, let me ask if this small example is clear.
Yes, and now we can see.
Okay, so in our next appointment tomorrow, that shall be, again, I want to say only by internet. In our next appointment, we shall consider the following question. Again, we have 2 dices. But we have to add our event is such that OMN such that the is 5, but under the following condition. M, the first number, is smaller or equal than 3. So we add at the end suitable condition. For example, suppose you participate in a lotto and you know that the third number is in some way, let us not explain how, in some way you know the third number is 32. What shall be the probability? Of course, you have additional condition, and it is important when you put additional condition to start to count your set under this condition. So this is so-called conditional probability, and the next lecture shall be devoted, connected with this conditional probability. Namely, we shall try to compute probability of event A, provided we have some condition B. We shall see how we can first see all possible cases of exits, some such that n is smaller than 3. So we count B, we count number of elements of A, and then we find the formula to compute probability of the event A under the condition B. This we shall do the next time. That's why here I plan to stop our recording and leave a little space for your question, and then to continue tomorrow. So I shall stop the recording, and if you have time for